Well, welcome back, everyone. Looks like we can make this official and get going. We're pretty much done with section 6.1. We're on the very last example. We're going to handle a new example where we're dealing with a midline equation. And for assignment 5, we've mentioned that the homework sets are going to be custom for section 6.1, 6.2, potentially 6.3 as well. So to find your problems, just click on the assignment. You'll find a PDF. And this is pretty much what they look like. I'm not going to do this for the rest of the course, but there's a couple sections where I just felt like the textbook didn't do a great job of what the actual objective was, plotting functions. And these are how I'm going to actually ask the questions in a real exam setting. So I felt like these questions are going to be a little bit better served for us doing them this way. That's a little bit more in line with how they're going to look like in the course. And it'll be the same thing for section 6.2. Thanks goes out to Mike, I believe, for spotting that the PDF was actually missing on this one. If you click on it again, the PDF is available. So these are going to be the questions for the next assignment as well. Also, I had to re-upload the assignment 5. There's a due date there that said something in July if you've already downloaded it. That was from a summer class. I just took the due date off of it to remove that distraction. The due dates are the ones that you'll see here. So we're getting through it, folks. One thing I should mention is graphing functions might not be your favorite topic in trigonometry. When I learned it as a student, it definitely wasn't my favorite topic. It was just something that you had to get through. The good news is we definitely get through it. After section 6.2, we'll be done with all of our graphing techniques and topics in this kind of stuff. Well, any last questions or any questions at all so far, folks, before we get started? Okay, well, let's give this a try then. We're really right back where we left off. Now we're taking a look at this function. Same instructions as before. We're going to look at amplitude, period, phase shift, the midline equation. And what these instructions are trying to get us to do is essentially this. This might not be a bad one to print off, just to have it available to help you out while you're doing problems. All those instructions there are trying to get us to calculate, again, amplitude, period, phase shift. Then the rest of this analysis is optional. Cycle start, this is the increment. All these things are really the minimal set of things you'd want to do to get a really excellent graph without too many points, too much work. So we're looking at really these two right here with all the instructions. It'll change for the new 4 functions as well. So let's give this one a try to start out. We want an amplitude to begin with. And let me just remind me what colors we used. Okay, we'll use green and blue for period phase shift. Let's keep that consistent. To start, for amplitude, it will be the absolute value of something. Any volunteers for what coefficient goes in there?
-2.
Good call, Hayes. So whatever is right here as a leading coefficient, it drops down in. And clearly, if it was positive, we wouldn't even need absolute value, but writing it down every time, even if you have a positive value, it's just a best practice, so we don't forget to flip it and write in a positive value for amplitude. So we're just pull that value in, drop it there, and we're all set. Next thing we want to hit is period. I think we use green for that one. To work with the period, we have to look at that coefficient there, the one multiplying x inside the function. We start off by putting down the period of the sine function itself. Sine and cosine have period 2 pi. Then we divide by whatever is here. So if that was 15, we'd have to divide by it. If it's pi, we'll just have to divide by pi. You definitely want to reduce these as much as feasibly possible. So write that in as a 2, and now we're in good shape. So the whole extent of our graph on the horizontal axis will have 2 units, is what this is telling us. For next bit, phase shift, this one's tricky because we have to do several things. We have to flip that sign right there, make this become a positive pi, but you still have to divide by the pi that's sitting right there as well. So whatever coefficient that is, will be represented in 2 places, period and phase shift next. So PS for phase shift is going to be, if it's negative pi, convert to positive pi. Then matching color coding, go to this pi, divide into here, and you've got your phase shift. So the phase shift is a +1. That means the whole graph didn't start at 0. It moved right by 1 unit, and it'll have an extent of 2 units when we plot over. Then there's one extra new thing. We solved this on all the other problems, but this time it's important and definitely worth credit. Because we're writing down an equation right here, one thing that you have to have is y equals. The y is telling you it's a horizontal line, and the equals right here tells you it's an equation to start. But then we need a number. Anyone see what the number should be right there?
5.
Good call. It's going to be this 5 is taking the graph that would have bounced around the horizontal axis. The midline equation was y equals 0, but if it's a +5, it's automatically a 5 right here. That one's new, so let's keep the yellow color coding just for that specifically, the fact we had a midline equation. Because we had a midline equation, plotting this is a little bit different, but it's actually not too bad. We're still going to say where the cycle starts, where it ends, and what the increment will be. Let's make that as our next steps, and then we'll start plotting this whole thing. Any questions to start us out, or first, before we go to the next steps? Okay, so here's the next important part. The plot will start exactly where you said your phase shift was. The phase shift is exactly at 1, so we'll start right here at 1. Then for the end, by formula, this one is going to be phase shift plus the period. It definitely feels like we're making a mountain out of it. You'll notice we wrote down these formulas every single time, but there's a strategy here behind all that. If you write this down every single time you have to plot a function, then by the time you go to take this as an exam problem, your fingers are probably going to want to write this down before you're even thinking it. It's just going to seep into your subconscious. The more of this stuff you write down, well, less those aren't as much formulas, but the more formulas you write down right before you use it, that's a really great way to memorize the formulas. You want to involve them as many of your senses as possible to try to absorb this stuff. But now that we're here, we'll just look up our phase shift. It's 1, so plug it in. Plus. Next is period. We just do another lookup. We're just using substitution repeatedly now. 2 substitutes in for the period. And that tells us the cycle is going to end at 3. Now, the next thing is the superstar, the increment. Like we said before, but we'll still say it now, this takes us to all of the most interesting places on this graph, maximum, minimums, and intercepts, as long as you're using this formula, 1/4 of the period, or 1/4 times p. So this will be 1/4 times, substituted in 2 for p. And again, you definitely want to simplify these as much as possible. This will turn into a half after canceling. And that's the increment in its simplest form. But now that we have a half here, you'll notice sometimes you don't necessarily want these completely simplified. This is better written in as a 2/2. It's just compatible with the 1/2 increment. And this one, where we end at 3, you might call this a 6/2. Again, it's compatible with the fact that our increment is a fraction this time. Sometimes that's not a bad idea. You want your increment as simplest as possible, and everything right here. But occasionally I make the start and the end fractions just because we're going to be adding a half to all those values, ending up at 6/2. That is optional if you keep it as a 1 to 3. I'll just assume you're really great at fractions and none of that bothers you. But if you feel like you're a little rusty on fractions and that kind of stuff, that's not a bad idea to convert these to the same common denominator as your increment. Well, if all that's said and done, here's what we're going to do next. We'll draw a horizontal axis. And I'm going to put stuff on here, but keep in mind we have a midline equation. Our whole graph is going up by 5 units. Still, it's worthy to build out the axis to start. So we're starting at 2/2. We're adding 1/2 to get to all of our next values. So add a half to 2/2 to get 3/2. Next is 4/2, 5/2, and it ends at 6/2. That's where we double check we're really ending at the right location. So we just added 1 to all the numerators here in short. So this is 1, 0 would be about here. And so our horizontal axis would be roughly in this location. Any questions, folks, with building up the horizontal axis at the moment? Okay, next thing we want to do is build out the midline axis. That's where the curve is actually going to be oscillating around. It's at height 5, so let's go 1, 2, 3, 4, 5. So that location is now our midline equation. If it's helpful, it's not a bad idea to just put down this horizontal line. And when you put that horizontal line in, think of that as just the new x-axis, essentially. That's what it's going to be bouncing around. That's the equation y equals 5 once again. So we have 5 here. Next thing we need to worry about is the amplitude. Amplitude of 2 meant something on the other graphs than it does here. Because we have a midline, amplitude of 2 means we go up 2 units to get to the peak, but that's from the midline. And then from the midline, you have to go down 2 units to get to the minimum. So let's put here, this goes up 5, 6, 7. I'll leave that with the pencil as 7, just to compare it with the amplitude. Then, because the amplitude is 2, go down 2 units, 4 and 3. That's where the minimum will be. So our whole sketch is contained within this band at height 7 and another band at height 3. We're just about there, folks. There's a lot to compare it or take a look at to get started on this. But the next thing we can say is, this is a sine function. It will start not on the x-axis, it will start right on the midline equation right here. So that's our first point. Ordinarily, sine goes up, but if you looked right here, you would have known there's a reflection on this graph. Sine is going to be going down to start on this one. So our next point is at 3/2 at height 3, so right about there. Oh, and I need to click on something to be able to draw, so it's right about there. So our sine curve went down, but that's the minimum we'll hit. So on the next increment, we're back to the midline. On the next increment to 5/2, we hit our maximum value. That's at height 7, so about here. Then the cycle ends at 6/2, so we're back to midline. So that's about what our curve will look like. Again, your curve doesn't have to be perfect, but if it looks like this, you could potentially lose a point. Nothing major, just a reminder that your curve shouldn't go like this. A sine wave is a nice smooth curve. There should be no points where you cut yourself on it, things like that. So it should come in more like this. Comes around, I'll put around like that. If it looks a lot worse, that's okay. Just make sure you round them out here and here. That's the major things I'd be looking for. Higgins asks, what did the negative in front of the 2 do again? Oh, thanks for asking about that. So if it was a positive right here, for example, then our curve would almost look the same, but it would start increasing. Sine would have increased to this value. That means it would have dipped down to this location, and it would look about like that if it was a positive 2 right here. But throw in a negative, and we're reflecting the whole graph. What we're reflecting across, though, is the midline equation right here. So that negative sign made it go like this instead. Any questions about that so far? Okay, did that make sense with that, the negative right there, Higgins? Awesome. Other questions so far? Oh, I think I already said that. Let's take a look here. Well, I guess we did it, folks. That's plotting sine and cosine. This is kind of like the worst case. It wouldn't be a good exam question, but you'll see this on a homework question as well, where you have to deal with a midline. Alex asks, could you go over how you figured out the amplitude and period again, and how it's used to find the phase shift? Yeah, absolutely. So for amplitude, what we took was everything that's right here. The entire leading coefficient goes in, and then we just take the absolute value of that to result in a +2 for amplitude. So amplitude is all about that. The short of it is just force it to be positive if it isn't, and you've got the right value. For the period, what we do next is, let me put this in black. I think I'll identify this a little bit better. The function sine itself has period of 2 pi, and so whatever goes right here, we just divide into it to get the result of period 2. After period, it's a little bit trickier with phase shift. Phase shift has a couple things going on. With the phase shift, we took the entire quantity, negative pi, and converted it to a positive right there. So we took the opposite value. Yeah, absolutely. Yeah, you could just call it pi and you got the right value. If it was a positive pi here, you would have had to put in negative pi instead. So just whatever the sign is, take opposite. Right, unfortunately, some problems might have a plus right here, which means it wouldn't match the original structure we're used to seeing. We still have to take the opposite of that value. But if it's a negative, yeah, you're pretty much just taking off that negative sign. So we did a couple things to get phase shift, the trickier part. We went right here, changed the sign, so we have pi on top. But the next thing is, you still have to divide by that pi right here. The same division for period is also a division in your phase shift. So that'll be a pattern that happens with each and every one of these. Does that help with running through our amplitude, period, phase shift? Awesome, glad to hear that. And the good news with these is I do award a lot of partial credit. Let's suppose this was a real exam question. If I make a mistake on amplitude or period or phase shift or all of the above, there's no way my plot is right. This is the incorrect plot. But out of a 10-point question, you might lose 3 or 4 points. If your plot is accurate, based off what you said here, you're still getting the majority of the partial credit of the problem. So I wouldn't be as worried about simple mistakes. Definitely try practice on the homework. On the exam, if you know how to construct a graph based off this, you're still doing really well. Other questions or so far, folks, before we go to the next section? Okay, well, let's turn over to section 6.2, where in these notes, we just went for sine and cosine. In the next section, we're going for cosecant, secant, tangent, and cotangent. But the good news is, recall that cosecant, for example, is the reciprocal of sine. If you're plotting cosecant, all you're really doing to a certain degree is recalling what the sine wave looks like and just building from there. So when we go to section 6.2, oops, there we go. That's exactly what we're going to do. If you want to plot cosecant, you really ought to plot sine first. So we're going to plot both of them on this graph and see what properties are for cosecant. We'll adapt them for plotting transformations of cosecant, just like we did with sine and cosine. Well, any questions before we get started, folks? Okay, well, we're doing a couple plots, so let's put in a pretty long line this time. I want the vertical axis to be really well represented. And let's start with this function. If you're going to plot sine x, well, you would say that the period is 2 pi. There's no phase shift here, so it's going to start at 0 and it's going to end at 0. There's nothing interesting there. But you would still want to use the fact that the increment that matters the most for this function is equal to 1/4 of the period, which would then be 1/4 times 2 pi. If you simplify that, that becomes pi over 2. So for the ordinary sine function, the fastest plot is just using pi over 2. Let's put that on the axes. So this will be pi over 2. On this one, call it either 2 pi over 2 or pi, your option this time. I'll go for the simplified version of pi, but you can visualize that as 2 pi over 2, meaning the next one is 3 pi over 2. And the next one after that is 4 pi over 2, reducing to 2 pi. It should have ended at 2 pi because that's our period. So now we have everything settled here. Next thing we'll put in is that the amplitude is 1 for the sine function. So that means on our axis here, we'll have a height 1. Let me try a little bit better. There's a trick that I kind of discovered. If your right's a little bit bigger like me, and you don't want your plot intercepting 3 pi over 2, make -1 about here, and it'll help out a little bit. +1 will be right about here. All right, now we're ready to plot sine. I'll plot that one in blue. Oh dear, I was going to do cosecant in green. Let me fix that real quick here. Here's -1, here's +1. And now finally, here's the sine wave. Sine starts at 0 because sine of 0 is 0. This has a positive coefficient, so unlike the last problem, it's increasing. Pi over 2, it's at height 1. Now it's decreasing. At pi, it's height 0. Still decreasing to -1 at 3 pi over 2. And starts increasing all the way up to 0 at 2 pi. So here's our real fast sine wave. This is not my best work, but it'll do. Doesn't have to be perfect. And now we're ready to plot cosecant. So this is kind of the fun thing about this. It seems imposing when you're thinking, wow, 4 more functions we have to plot, and sine and cosine was tough already. But plotting cosecant is just a review of plotting sine in a real sense. Here's what we can do next. After I fix that color coding. Now we're on cosecant of x. That means y equals 1 over sine of x. That's actually a really helpful point of view for us to take. Because whenever sine of x goes to 0, that's a 0, we have a vertical asymptote immediately. It went to 0 here, so there's a vertical asymptote overlaying the y-axis. I'll write it in like this just to emphasize. We consider the vertical axis as part of the plot, but when you're doing the dashed line, I'm okay if you just do a dashed here or just neglect it and realize there's a vertical asymptote here. Next vertical asymptote is right here, because you can't put pi in that location. Sine of pi is 0, that's 1 over 0, which results in another vertical asymptote out on the graph. So it starts at a vertical asymptote, it has a vertical asymptote right in the middle, and it will end on a vertical asymptote from right here. Now, next thing we can say is, what about at pi over 2? If you ever calculated cosecant pi over 2, we'll observe all you're really doing is taking 1 over sine pi over 2. Sine pi over 2 is exactly 1. I mean, we see it right here. Blue is the sine wave, and at pi over 2, it had height 1. So right here, we have 1 over 1 equals 1. But what does that tell us? There are 2 points on blue that directly match up with cosecant. One is right here, and the other is way down here by the same trick. So cosecant matches here and here, but nowhere else. Cosecant is repelled away from the blue curve. And by repelled away, we mean like this. It's repelled from the blue curve, but attracted to the vertical asymptote. So it takes that shape, and it's symmetric around pi over 2. So it takes, well, visualize that as perfect symmetry, that shape going to the left. It looks kind of parabolic, but it's not a true parabola because it's constrained within the vertical asymptotes. Real parabolas are free to go far to the right, far to the left forever. So we're repelled away in this stage for cosecant. We're also repelled away over here with cosecant, and the curve goes like that. So this is the plot of y equals cosecant x. Kind of a crazy plot. It's going to have vertical asymptotes. All of our other trig functions have vertical asymptotes aside from sine and cosine. But any questions at all, folks, with getting that basic shape?
Do we have to draw the arrows for the cosecant too?
You mean these arrows right here?
Yep.
I would say that's optional. That's more of me indicating it's going up forever. If you neglected to put that down, I'd say that'd be all right.
Also, like, do we need to use in different colors on the exam and such because we're only offered pencils.
No, you can use wood, you can use just
Okay.
pencil and that would be fine. Yeah, you don't have to do the color coding. Color coding is more for making the notes more readable, I'd say.
Okay,
Other
thank you.
questions? Yep, you betcha. Okay, well, let's take this information and we're going to plot that thing. Twice cosecant of 2 pi times x plus pi. That sounds awful, but the strategy we use on the last notes works really well on this one. The strategy would be get an indication of where all these 5 different points are. The first point is a vertical asymptote. Second point is a point on the curve, which generates cosecant. Then it's asymptote and another point generating. So as long as you know this basic shape in green, you're solid, you're ready to go. Also, we have to have good knowledge of what we did in the very last section. Math is kind of like a stack of cards in that way. So let's put that screenshot down here just for quick visual reference when we need it. Now let's give this transformation a try. It says, and these instructions will be verbatim on the homework as well as on a real exam. For each function, do the following. Notice what it doesn't state. It doesn't ask for the amplitude, just period and phase shift on this one. So we'll get that period in and that phase shift. And the reason there's no amplitude is your function had to be bounded in order to have an amplitude. Sine is bounded between -1 and +1, but cosecant is unbounded. It goes up forever and down forever. That means there is no amplitude for this graph. And you would also know that if you were looking, say, right here, we're on the cosecant row. I put these two in red because this is unusual. Most of the trig functions have no amplitude, so that's a red flag in a certain sense. This is what's typical. Amplitude is just going to be undefined. But you know what? It's still important. So that 2 right there is still going to be a part of our graph. We'll show how to use it. But next, let's take a look at period. For period, we use the period of the cosecant function. Cosecant has period 2 pi, just like sine. So just like we did with sine, we put 2 pi in the numerator, and we look at whatever the coefficient right there is, the leading coefficient of x inside the function, divide by that, and we're on our way. So the period on this function is exactly 1 this time. Any questions to that stage so far? Okay, well, now that we have period, the next thing we need is phase shift. And I'm color coding not just pi, but also the sine, because once again, sometimes this is the easiest thing to miss on these kinds of problems. Phase shift is going to be -pi. And then that's not the whole story. It's also divided by 2 pi right here. So if you divide by 2 pi for the period, you will also divide by 2 pi for phase shift, each and every time. So that's a nice pattern that just stays solid for us each and every time. Reduction will just give us a -1/2 here. And let me hide that graph just for a minute. So we've got it. We have period and phase shift. It says to plot the function over one complete cycle. We want positions of the vertical asymptotes. So we'll put in dashed lines going up. We'll also indicate the y-axis, its values to indicate the scale in the graph. And that's where the 2 is going to come into play. So here's how the sketch starts. Or before even doing that, let's go to this. The start of our graph. The formula here hasn't changed. It's still phase shift. This formula does change though. So we'll make a really big deal out of it when it happens. When we're plotting secant, this formula is no longer the same. That's kind of a surprise. But here it's still just the phase shift, and that came out as -1/2. Put that in blue just to match up that color coding. So next, the end will be phase shift plus the period. So we'll look up phase shift. That one's -1/2. Add to it the period. And notice our period is a 1. That means if you like, you could just convert this to a 2/2, which is a good call. That will match up the denominators. And we'll have that our end is going to be right at 1/2. So it looks like the domain is symmetric. It starts at -1/2, and then it goes and ends at +1/2. We're symmetric about the origin, going the same distance to the left and the right. Only thing remaining is we need to know our increment. This one hasn't changed. It's 1/4 of the period, but it will change for tangent and cotangent. But for here and now, we'll take 1/4, multiply by the period of 1, and we've got it. That's kind of a nice period to deal with. It's just a 1/4. However, because we have a fourth, we're going by quarters. Let's go up here and right here and multiply by 2/2 just to match up our denominators. So this one will be -1/2 times 2/2. We'll start at, oh dear, that's not quite right in the numerator. Let me try it again. We'll start at -2/4. And by the same token on this one, multiply by 2/2. We'll end at 2/4. Ran out of space to show the operation, but same as before, multiply by 2/2. So all of this is just the preliminary analysis that's going to give us the sketch as fast as possible. Any questions with either the left side or the right side?
Could you remind me where you got the negative pi at again?
Absolutely. So it comes from right here. And again, this is to me one of the trickier parts of the whole preliminary analysis. Whatever you have right here, you always take the opposite sign. Yeah, that's what we did right here. That's the negative we put in front. Exactly. In the formula sheet, if you put f of x equals 2 cosecant 2 pi x, the formula had a minus there. And so if you put a minus, well, you can put in an extra negative sign here. And that gives us the original function back, exactly. So if you view it that way, that's the reason why we're always taking the opposite. We're forcing the function to match the original formatting of the formula sheet, like you were mentioning. So you can view it this way, or with over here, just flip whatever sign you see, and you're doing the same kind of operation. Does that make sense, Orlando, on that idea there?
Yeah, that works. Thank you.
You betcha. Other questions so far? Okay, I think we're ready to start. We have a graph down here, just in case we need to call on it. And we have all the interesting information we need, except one piece. Right here, when it says label the y-axis to indicate its scale, nothing here that we've written down supports it, but there is something about the function that will do it for us. If we go up or go down, we plotted sine this way, and sine had amplitude 1. Well, if this was a sine curve that we're plotting side by side, it would have had amplitude 2. So we're going to use that as the scale, and all we're really going to do is put a 2 there and a -2 there. So that gives us our vertical scale. Always comes from right here. At this stage, we're ready for the plot. Let's go about like this. First, let's do the y-axis, since that's the most interesting bit, I'd say. You'd probably want to put it more closer to right around here and right around here, I'd say. Now we've got our values in. Next thing we can do is put in our start. It's at -2/4. So I'll go 1, 2 tick marks to the left. Let's call that -2/4. Add 1/4 to all these quantities. So here will be -1/4 going to the right. Over here is, well, 0/4. We did add 1/4 to it. Next tick mark is +1/4. And finally, it ends at 2/4. So now we pulled in this information to get the horizontal scale. But let's definitely highlight in yellow that. Getting the y-axis in is really just a callback on amplitude that doesn't exist for this function, but we're using it because That's the amplitude for the guideline curve, the sine wave, the one you see in blue right here. It would go into those two locations. Does that make sense to folks on how to go from here down to here? Okay. Next thing we're going to do is not plot the sine wave. That's helpful for starting out, but we're focusing more on cosecant. But what we do know is we will start on a vertical asymptote. There it is. There'll be a vertical asymptote in the middle and a vertical asymptote on the end, each and every time. And you'll also notice each and every time there's 5 key points. Here's 1, 2, the origin is the third, kind of hiding, 4th and 5th. So this is a process that always works. Now, we have to be a little bit careful. The sine wave that's the guideline could be flipped. Let's take a look. That's a +2, so it's the same kind of guideline we're using. And these are the points I would put. We're not plotting the whole thing in blue. We're going right up here. We're just putting a point down. Then right over here, we had the vertical asymptote. Then we go right down here and we put a new point down. Let me do some rearrangement first. Let's put the 4th over here. And here's the next point. So these 2 points in black are from this original sine wave. And if it does help, there's no harm in putting just a really light line that goes like this as your sine wave. It is a distraction, so make sure it's light and that you emphasize this one. This is finally cosecant going up and to the right. Up and to the right. Cosecant is always repelled away from the x-axis, is a way to think about this as well. So it had no choice but to go up. At this point, because it can't hit the x-axis, it has no choice but to go down. So there it is going down. Essentially, this curve in black is just like the one in green, but we've changed the domain, or excuse me, we've changed the range we're plotting over. We're going from -2/4 to +2/4. And the range has changed. It's going from 2 to infinity, -infinity to -2 on this one. I think we got it, folks. That's the adventure of plotting a cosecant function. Any questions about it so far? Okay, this is a lot of plotting. It's nice that it kind of falls back to how you do your sine work right here. Let's delete that just so it's not too distracting if you come back to the notes. But one thing you might wonder is, why do we focus on so much of this plotting work? Let me put down just a really quick explanation. So if you're like me and you're not sure why we do all this, here's one good justification. Imagine that this happened in a different problem. You're told to solve, let's take the function, 2 cosecant, 2 pi x plus pi equals, let's say it's 1. You're told you need to solve that equation. Well, if you have an inkling of what the plot looks like, maybe you didn't even sketch the whole thing, but you knew, well, there's going to be vertical asymptotes. The cosecant function doesn't even get close to the x-axis. It's repelled away. And if there's a 2 here, there's no value can hit between -2 and +2. You could say immediately, no solution. Why is that? Well, if there's a +1 right here, it would plot this way. Here's y = 1. Observe, cosecant never intercepts that line. That means there cannot be a solution at all. If instead it looked like this, y equals, let's say it's like a, how about a 4, something like that. Well, there will be infinitely many solutions. Here's 2 right here. And this is a periodic function. It replicates. There'd be 2 more over here. We wouldn't get 2 over there, but then we get another 2 more. There's infinitely many solutions now. And we would know this because we know 4 is now in the range from 2 to infinity, where we can intersect with the curve. Those points of intersections give us values down here, and those are the actual solutions to those equations. So the major thing to take away, I'd say, from all of this, the major purpose is, it's really interesting that you can just write down an equation and go to your mental chalkboard and know whether or not it could even be solved before even beginning working on it. to me, that's the bigger takeaway of why all these plots are pretty helpful to have in algebra. But any questions at all, folks, with
But
either the,
why can it be solved? Because if you put the line for like y is equal to 4, then isn't it like multiple answers?
yeah, so if you have a, sorry, if you have a y equals, we'll delete some weird stuff. There we go. If you have y equals 4 here, and this is a 4, I should have went like that and said there are solutions. But if it looks like this, with the 1 specifically, this is the one that had no solution.
Oh.
Make sense, Hayes?
Yeah, thank you.
You betcha. Yeah, well, I should have put here when I put a 4, I should have scratched that out. That would have had infinitely many different solutions, like you mentioned. Other questions so far? Okay, well, that's how we plot sine and cosecant together on this one right here. And if you look at this document, here's where we are. Everything's kind of nice about this function, and we're about to do secant. This is the trickiest function in the whole set. It's got a lot going for it. It does not start on the normal position at all. This is a good formula just to be familiar with, because it's good to know if you're doing secant, this is the first pretty problematic function to plot. So let's take a look at how all this goes, and we'll do our overall sketch when we come back on Tuesday of next week. First, we need to see what the issues are for this thing. So on our next problem, we're turning over to graphing both cosine and secant on over one complete cycle. Let's color code these like we did before. I'll do cosine blue, secant in green. And just like before, cosine has this for an increment. We're going to go a distance of pi over 4 to get to all the useful values. So starting at 0 right here, we'll have a value of pi over 4. We'll have a value at pi over 2, or 2 pi over 4. This one will be 3 pi over 4. Or hang on. Sorry, I think I got the wrong increment on this one. Let me try one more time. The increment, let's write this one out carefully, should always be 1/4 of the total period, which means it's 1/4 times 2 pi, which means if we work this one out carefully, it's pi over 2. Sorry for the distraction on that one. Pi over 4 is not quite the right quantity. We want to go a distance of pi over 2, just like with secant and sine. So this should be pi over 2. This should be pi. This one's 3 pi over 2. And you know, ordinarily, we'd go over to 2 pi. Let's put that on there. But we're actually not going to use it. It's kind of surprising in a way. What we're actually going to do is go backwards by one step to negative pi over 2. And there's a reason for that. It's kind of a distraction. But let's start plotting cosine to show what the reason is. First, cosine has an amplitude of 1, so I'll put it here and here for a -1. Now, if we put in 0 for cosine, cosine at 0 evaluates to 1, so it starts at a peak. That's our problem. The fact that it started at a peak means we need to make an adjustment. But let's keep on plotting to the right to see what else happens. At pi over 2, we have a vertical asymptote right here, so let's plot it in. Whenever the curve hits the x-axis, we invoke a vertical asymptote immediately, algebraically. Then next at pi, cosine at pi is -1. So here we're taking a minimum value. Here we're back to the x-axis. Cosine at 3 pi over 2 is 0, so automatically there's a vertical asymptote here. Now that's the problem. If we plot on this domain, our graph is going to look really, really weird. It's not wrong. It's the right graph. It'll have all the right features we need, but visually it's so disconcerting that people decided a long time ago, and they just seem to make it consistent, that we'd rather plot along this line. That's the better domain to plot. And why is that? That's because cosine at negative pi over 2 is also 0 right here. Which means if we start there, we're starting on a vertical asymptote. And that's the tradition, that you always start with a vertical asymptote, whether it's secant or cosecant. There'll be a vertical asymptote in the middle, and that you'll end with a vertical asymptote. Looking at this again, negative pi over 2, well, if 1/4 of the period was pi over 2, negative 1/4 of the period is negative pi over 2. That's where this comes from. The negative 1/4 of the period is where the cycle should start, because that's where the vertical asymptotes start. And our graph is going to look pretty crazy if we didn't do that kind of convention. So that's the only reason that this is such a complicated plot. Cosine didn't start at a vertical asymptote. But here's the rest of cosine. Comes up, around like that. And observe, because we're starting at negative pi over 2, it looks just like a sine wave. That's what it should look like, because it's a co-function to the sine. All it is a phase shift of it in a certain sense. Cosine and sine are essentially, in a real sense, the same function in those terms. But we've got it, folks. We're plotting along this region for our cosine function. That means we can use the same exact tricks for plotting secant that we use for plotting cosecant. We go right here. That's a point that matches exactly. Let's work it out just to be sure. If we calculate, say, secant at 0, we need to recall secant is 1 over cosine. So it's 1 over cosine at 0. Cosine at 0 is 1, so it's 1 over 1, which means it's 1 exactly. So we match here. By the same exact token, we match here at pi, negative 1. Then the rest of the curve goes like this. It looks almost the same as the cosecant curve. The only difference is where we started the cycle. We're starting right here, and that's the worst part of the function, recalling that that's where we have to begin. But here it is, folks. This is our good old y equals secant x as a function. Any questions with that one so far? Okay, and just for a quick visual, let's make Desmos plot it.
So it looks like the same thing as cosecant, just in
It
like
does.
different domains.
Exactly. If we put both, say, y equals secant x and y equals cosecant x, just like you said, it's over different domains we're plotting. Same exact curve, right? Blue is cosecant. Red is the secant curve we just plotted. Let's put in y equals sine x. I like that. So notice sine x is matching up with the secant. Let me double check. Cosecant curve in blue. We put in y equals cosine x. It's getting busy at this point. To be completely honest, I have to look at the colors. Here's secant in red, cosine in purple. That's what they all look like. But let's go to that awful one again, the one we just plotted. And let's suppose we plotted it from 0 to 2 pi. 0 less or equal to x, less or equal to 2 pi. Here's what the plot would have looked like. It would have looked totally different, right? Versus our cosecant, if you plotted on that domain. It's a confusing looking sketch. And for some reason or another, people are so uncomfortable with that, they change the domain by going negative pi over 2, 3 pi over 2, and now it looks just like a secant, aside from the fact that it's been shifted over. So those are some really weird functions. We'll come back to this one and this issue right here, plotting it carefully when we come back on Tuesday. But any other questions or comments at the moment, folks? Okay, well, we're nearly through, folks. I'd say at this point, we're a third away from plotting. And the good news is that cosecant and secant, they're not bad aside from that. These are, in a certain sense, brand new plots because you'll observe the period has changed on these, and so has the increment. And at the same time, tangent has cosine in the denominator, just like secant. So both of those start at really wonky spots, just to make the plot look a little bit more palatable. So we're not dealing with, well, the other one we had on there. Well, that's definitely all I have for folks. We'll be right back to example 4 next Tuesday. Have a great weekend, folks. It is President's Day, but we'll be back for our class on Tuesday. But have a great President's Day as well.
Thank you. Good night.
Thanks, you too.
Thank you.
Have a good one, folks. Oh, and I forgot to mention, if I haven't gotten your exam back, don't hesitate to email me. I don't have any qualms about scanning it and getting it back to you. Well, at least it's in the recording. And for the folks that did hear that,